Okay, picture this. You build a mobile app on your high end development laptop with exactly 5 test users in your database. It runs flawlessly. Butter smooth, 60 frames per second, you ship it. A week later, a user with 1,000 synced contacts opens your app. Their phone turns into a literal hand warmer. The UI freezes, the frame rate drops to absolute zero, and they delete your app. What went wrong? You didn't write broken code, you wrote unscalable code. To prevent this, engineers use big O notation. It isn't an academic hazing ritual meant to gatekeep tech interviews. It is a mathematical rating system for how your code behaves as the data grows. Before we look at the performance ladder, let us define exactly what we are measuring: time complexity and space complexity. When people hear time complexity, they assume it means counting the exact number of seconds or milliseconds code takes to run. It doesn't. Execution time changes based on whether you run code on an old smartphone or a multi-million-dollar cloud server. Instead, time complexity measures the number of operational steps the CPU must take relative to the input size, n. It tracks how fast the workload grows. Space complexity, on the other hand, measures memory allocation. It's not just the size of your raw code file, it tracks how much additional RAM or temporary storage your algorithm forces the computer to allocate while it's actively processing the data. Moving ahead, we are going to have a look at the complexity ladder from baseline efficiency to architectural disaster. Let us start at the absolute base of our performance scale, O of 1, or constant time. When an operation is O of 1, it means its execution time remains completely flat, regardless of how much data you throw at it. It takes the exact same fraction of a millisecond whether your database contains 10 rows or 10 million rows. Think about an app like WhatsApp. When you open a group chat and click on a member's profile, the app doesn't scan through its entire global user database to find their profile picture. Instead, it looks up the user via a unique ID using a data structure called a hash map. Because it maps a direct connection between the ID and the data, the lookup is instant. If you're building features like checking if a user is logged in, retrieving a balance in a banking app, or grabbing an item out of the cache, your goal is always O of 1. It is the most predictable, efficient code you can write. Next up is O of 1's closest competitor, O of log n, or logarithmic time. In a logarithmic algorithm, every single step your code takes cuts the remaining dataset in half. It is incredibly powerful because as your data grows exponentially, your execution time only grows linearly. Think about how search functionality works when you're looking for a specific movie on Netflix. If Netflix had to scan through every single title in its catalog line by line from A to Z, searching would feel painfully sluggish. Instead, databases use sorted search trees. If you type in a movie starting with the letter M, the system instantly discards everything from N to Z in its first calculation. It cuts its search window completely in half, then does it again and again. Because of this halving effect, even if Netflix adds hundreds of thousands of new titles to its platform, a logarithmic search query might only take 2 or 3 extra microsteps to find what you're looking for. It scales effortlessly. Moving up the ladder, we hit O of n, or linear time. This is your standard everyday engineering workhorse. Linear time means your execution speed scales in a direct 1:1 ratio with your data. If your dataset doubles, your execution steps double. A great example of this is the top bar on Instagram that shows your friends' stories. When you open the app, The code has to look at the list of accounts you follow and check a Boolean flag for each one. Has this user posted a story in the last 24 hours that you haven't watched yet? If yes, draw a colorful ring around their profile picture. If you only follow 20 close friends, the app runs 20 quick checks instantly. But if you are following 2000 creators, the software has no shortcuts. It has to step through all 2000 accounts one by one to decide who gets a ring. Now, an obvious question comes up. What if the first person in our feed has an unread story? Doesn't the loop stop immediately? Well, yes, for that one profile. But to render the entire top bar, the app can't just stop. Plus, as engineers, we calculate performance based on worst case analysis. We assume the universe hates us and the unread story is at the absolute end of the list. Or we have all been watched. If your code has to check a collection from end to end to build a complete UI state, it is always rated as O of n. Now we cross into the zone where code starts breaking in production. This is O of n square or quadratic time. With quadratic time, if your data doubles, your execution time quadruples. If you pass 1,000 items in an O of n square function, it takes 1 million operations to operate. This is almost always caused by nested loops, meaning a loop executing inside another loop. Let us look at a social app feature like contact syncing. Suppose you upload a list of 1,000 contacts from your phone. The app wants to find which of those contacts are already mutual friends with each other. If the developer writes a naive solution that takes the first contact, runs a loop to compare it against all 1,000 contacts, then takes the second contact, runs another loop against all 1,000, and so on, that is O of n square. On a fast developer device in an office, you won't notice a lag with a small test group. But the moment a real world user syncs a large contact list, the phone's main thread chokes. The frame rate drops to zero, the UI locks up, and the operating system might force quit the app for being unresponsive. At the absolute top of the danger ladder is the O of 2 to the power n, or exponential time. This is where execution growth doubles with every single extra item you add to the input. To put the math in perspective, if an exponential function takes a few milliseconds to process 10 items, processing 30 items can take days and processing 50 items can take centuries. You almost never see this intentionally used in a standard app feature because it is mathematically devastating. It typically happens by accident through unoptimized runaway recursive functions, like trying to calculate a complex nested hierarchy or password cracking algorithms without optimization. If an O of 2 to the power n function hits your production servers, it acts essentially like a self inflicted denial of service attack. It will take your backend down. Now that we understand the ladder, let us talk about how this dictates actual system architecture. In the real world, you can rarely optimize for both time and space simultaneously. Every major software system is a balancing act of trade offs where the hardware limits enforce your design choices. Let us look at a high frequency trading software. These are the systems used by Wall Street to buy and sell stocks in milliseconds. In this world, a single microsecond of delay costs millions of dollars. Time complexity is only metric that matters. To achieve absolute O of 1 instant speeds, these systems pre-allocate massive blocks of memory and load gigabytes of data into RAM before a trade even happens. They willingly burn massive amounts of hardware space just to save a few CPU nanoseconds. But Look at the absolute opposite end of engineering: embedded software, like the code running a medical pacemaker or a car's anti lock braking system. These tiny computer chips operate on severe physical space constraints, sometimes having less than 32 kilobytes of total memory. If the software runs out of memory, the system crashes, and in a pacemaker or a car brake, a crash is fatal. In this environment, you don't have the luxury of caching data in memory to make things fast. You are forced to write code that takes a few extra CPU steps, meaning it has a slightly higher time complexity, solely to guarantee that its space complexity never exceeds the rigid physical memory limit of the hardware chip. But demystifying these concepts is just a first step. To write production grade code, you need to know how to fix these complexities when they inevitably show up in your code reviews. Instead of waiting for the next video, you can jump right ahead. I have put the link to the resources I used for this video in the description below. Be sure to have a look at them. See you in the next one.